Hi fellow experimenters. AI6MK here. Welcome to my lab. Have you ever wondered if your counters or signal generators were accurate, or are you just fooling yourself? A Gpsdo will take the guesswork out of determining the accuracy of your equipment. For those of you not familiar with Gpsdos, the name refers to a GPS-disciplined oscillator. The accuracy is several orders of magnitude better than even the most stable crystal oscillator. Accuracy is better than 1 part in 10 to the 10th. It's an inexpensive, very high accuracy oscillator, typically providing outputs of 10 MHz and 1 pulse per second. You can buy these units on eBay for about $150. They are made in China from salvaged OXCOs, oven-controlled crystal oscillators, used in cell base stations. The one I bought uses an OXCO made by Oscilloquartz. The Gpsdo includes circuitry to lock onto the atomic clocks used on the GPS satellites. The latest GPS satellites typically has 3 cesium atomic clocks on board, which are synchronized to a master atomic clock on the ground. Since it receives RF signals from GPS satellites, the Gpsdo does require an active external antenna. However, no special location is required. Mine has been working fine with the GPS antenna indoors. Even with the loss of GPS satellites, the Gpsdo maintains a last known good set of conditions to maintain a high accuracy 10 MHz output. Here is the output waveform of my Gpsdo on a scope. As you can see, it's a sine wave and produces about 420 mV peak to peak, or minus 3.6 dBm when terminated into 50 ohms. Here you can see the internals of the Gpsdo. The OCXO is a double oven type. It looks very well made to me. External connections are 15 volt to 24 volt power, with BNC connectors for 10 MHz and 1 pulse per second outputs. The GPS antenna is connected using an SMA connector. Be careful not to short it out, since the center of the SMA connector is powered. You can use the Lady Heather software by connecting a PC to the RS-232 connector, but I was not able to get this to work. Probably just pilot error on my part. The 3 indicator lights show power, 1 pulse per second and satellite acquisition. The red 1 pulse per second light only blinks when the unit has acquired sufficient satellites for accurate operation. This, and the next slide, show an HP8648A signal generator and an HP5342A frequency counter. The HP8648A signal generator is a low-cost unit using ATCXO as its internal frequency reference. Of course, low cost for HP is still very expensive, and I was able to purchase it cheap on eBay and repair it. It's very well made, apart from the OEM power supply, which is junk. Details of the repair for another day. My 5432A frequency counter is an older unit, but it has option 1, a very stable OCXO internal frequency reference. As is standard on HP instruments, and most other quality instruments, the rear panel has BNC connectors to connect an external high-precision frequency reference. These rear panel BNCs will be used in some of the following experiments used to illustrate the use of a Gpsdo. Okay, so on to the interesting stuff. Experiment 1 connects the output, the signal generator, to the frequency counter. Both signal generator and frequency counter are using their internal reference oscillators. By the way, I left both instruments powered up overnight, to stabilize. The signal generator is set to a frequency of 435 MHz at an output level of 0 dB. As you can see, the frequency counter reading is pretty close to 435 MHz, but is 16 Hz too low. So the burning question is, which one is correct? The answer is, I don't know. Both are probably wrong. However, the OXCO internal reference oscillator on the HP5432A frequency counter is of higher quality than the TCXO on the HP8648A. So, if I had to guess, I'd say the frequency counter was correct and the signal generator was slightly off frequency. Experiment 2 uses the 8648A internal frequency reference for both the signal generator and the frequency counter. The rear panel connection using coaxial cable is shown on the slide. The result of experiment 2 is shown in the slide. Wow, the frequency counter reads exactly the right frequency of 435 MHz. How can that be? How can this be any more accurate? We are still using the same hardware as experiment 1, just connected differently. The answer is no, this is not more accurate than experiment 1. In fact, the combination uses the Gpsdo from the signal generator as a common reference oscillator. It's easy to be fooled by this configuration. It's basically just checking that the digital logic in the signal generator and the frequency counter are operating correctly. Experiment 3 is very similar to experiment 2 but uses the 5342A internal frequency reference for both the signal generator and the frequency counter. The rear panel connection using coaxial cable is shown on the slide. The result of experiment 3 is shown in the slide. Again, the frequency counter reads exactly the right frequency of 435 MHz. How can that be? Is the signal generator outputting exactly 435 MHz? We are still using the same hardware as experiment 1, just connected differently. The answer is no, but is probably more accurate than experiment 1. This time the combination uses the more stable OXCO from the frequency counter as a common reference oscillator. But again, it's basically just checking that the digital logic in the signal generator and the frequency counter are operating correctly. Experiment 4 uses the Gpsdo as the external reference oscillator for the 8648A signal generator. The 5342A frequency counter is using its internal OCXO reference oscillator. The result of experiment 4 shows the frequency counter is reading the exact frequency set of the signal generator. So, is this more accurate than experiment 1? Yes, with the Gpsdo locked onto the GPS satellites, we can be confident that the signal generator is outputting the desired frequency of 435 MHz. I had previously calibrated the OCXO on the 5342A to the Gpsdo by monitoring both waveforms on a scope. I was able to adjust the OCXO until the waveforms were almost in sync, with a very small error of 0.025 Hz. By the way, I was hoping to use the Gpsdo as an external reference oscillator for the frequency counter, but the output is insufficient to drive it. I'm working on a distribution amplifier to provide multiple 2x outputs from the Gpsdo. So, here are my conclusions. After locking onto GPS satellites, the output of the Gpsdo is 10 MHz to very high accuracy. Of course, I don't know this for sure and this is an assumption. The unit is inexpensive and easy to use. Of course, $150 is not cheap, but alternatives are currently very expensive. Rubidium frequency standards are available for lab use, but they do drift a little over time. The U.S. Air Force manages the GPS constellation and works 24/7 to keep it accurate for civilian and military users. Connecting a Gpsdo to HP equipment is very easy using the rear panel BNC connectors and coaxial cable. The Gpsdo starts up very quickly and provides an accurate 10 MHz after only 10 minutes. An external antenna is required to connect to the GPS satellites. The power consumption is only 5 to 6 watts, so can be left on continuously. Takes all the guesswork out of calibration for lab equipment. Awesome hardware and I strongly recommend you get one for your lab. This was a great project and upgrade for my lab. I learned a lot and I hope you learned a little too. Thanks for watching.